Hello everybody. So we are back again in our class. So today what we'll do, we'll be going for one very important thing in plasma, that is plasma screening. This plasma is called quasi-neutral. This is because plasma is macroscopically charge neutral, but if you go deeper and deeper, I mean smaller and smaller spatial scale, then below certain length scale you will see that the charge neutrality doesn't hold anymore. There is something called Debye length. You might have heard already Debye length. So this is the minimum length scale within which the charge neutrality holds. If you go inside, suppose you assume a sphere with a diameter of a Debye length, then if you enter inside that sphere, you will no more feel that the system is charge neutral. It is very natural because suppose the plasma is consisting of charge particles only and they are separated from each other. And if you go very close to any charge particle, it is quite natural that you will see the Coulombic field of that charge particle. So, depending on the kind of plasma that you have generated, this length within which you find that the charge neutrality is not holding anymore, beyond which charge neutrality holds, may vary. So, it is quite interesting to know, to find a mathematical expression for such Debye length within which the charge neutrality will be maintained. So for that actually we need to do some mathematical derivation, and we will use only our school standard mathematics to tell you where we are arriving and what may be a right expression for this Debye length. So what do you do actually? Let us consider a distribution of electrons and ions, somewhat random kind of thing as I have shown on the lower right corner. So this is quite a good number of electrons and ions. They are more or less making an assembly which is neutral, charge neutral. And in that, what we are doing, we are introducing a plus Q charge inside that assembly, and we want to check whether this plus Q charge will be shielded by the other charge particles, or if it does, then within what distance will not be seeing, after what distance will not be seeing the influence of plus Q at all actually. So let us start. So once the charge is inserted, there will be a distribution of potential because of the charge, and there may be different form. We don't know just now what is the form of that potential will be. You know that if it was a pure plus Q charge and there was nothing inside, then you would be confidently telling that it will be Coulombic potential. There is no doubt. But now the situation is different. The charge is now surrounded by a number of positive and negative charge particles. You know that when the charge particles are distributed inside that, the velocity distribution, we can assume that number of particles will be following that kind of thing, that the first equation that I have given. If E is the energy, then E of course consists of this kinetic energy and potential energy. And the potential energy definitely phi minus phi 0, where phi 0 is the potential which would be there far away from that plus Q charge, where no effect of plus Q is reaching. And use the speed, of course, and if it is a Maxwellian distribution, you know that if you formula 4 by n m by 2 pi k t to the power 3 by 2 to the power mc square minus mc square by 2 kt c square dc in cdc. There is a number of particles in c and c plus dc. So that is there, and then it is natural that because I have inserted a plus q charge particle, density of electrons will be more as we go closer to plus q, and positive charge will try to go away from that plus q charge because they don't want that, they repel that thing. So as you go closer, there will be more electrons than ions present there actually near the plus q charge. But then why the electrons just simply doesn't go and sit over the plus q charge that I have inserted? That is mainly because of the thermal motion. So thermal energy doesn't allow it to sit over the positive charge. So that is the case, and we can assume the distribution of this electrons and ions as I've shown on the bottom right expressions. So n equal to n0 exponential of e phi minus phi 0 by kt, because that minus sign and minus electron charge, negative electron charge, that has resulted in the positive value in the exponent, and the bottom one is for the ions, that is the distribution. Now, for any existing electric field, for any change when you do, then electrons being very lighter, how much lighter? It is 1836 times lighter than proton, and many protons are there in the atoms. So you can understand that in that respect, atoms are very bulky, ions are very bulky compared to the electrons. So once a field changes, the electrons adjust themselves, rearrange themselves very quickly as per the field. But ions do not become able to, they do not become able to redistribute them in that fast actually. So for that time actually you can assume that this for the electrons movement, the ion background is more or less stationary. That is, Ni is same as N0, which was existing earlier before you inserted the plus q charge. So if that is the case, then we now can calculate the charge density because of that rearrangement of the electrons and ions. So it will be definitely density of ions minus density of electrons. And if we do so, then it is coming to be, you see that n0 into 1 minus exponential, because Ne, if you go to the previous slide, then we have obtained the expression for Ne that we have just put over here, and we find, and Ni you have taken just as n0 because as I told you that electrons are moving so swiftly that for all practical purposes the ionic background is more or less static for the movement of electrons. So this results in the Poisson's equation del square phi equal to minus rho by epsilon, and because of the theta and phi symmetry, you can write this expression in polar coordinate with only radial coordinates. And of course you know that for plasma to form this thermal energy must be much higher than the Coulombic potential. Otherwise this charged particle will just club with the electrons and there will be no plasma existing over there. So this E phi by kt much less than 1. So that is a very reasonable estimate. So if we do that expansion with that E phi minus phi 0 by kt much less than 1 assumption, then what we are getting on the right side of the Poisson's equation, n square epsilon 0 kt into phi minus phi 0. Now when we are expanding this potential equation in the radial coordinate, you have landed up with an equation. I am sure that some of you are thinking that it can be solvable, some of you are thinking that how it can be solved. Now I will tell you a very simple way to find it out, the solution of this equation. So here I go. The equation that we got, we can write it in the form that is on the upper right corner. Okay. So the same expression we can write exactly in this form. If you are in doubt, you can just expand the left hand side of the first equation on the upper left corner and that of the upper right corner, and you will see that the expanded version is resulting in the same thing, same expression. So they are essentially the same. But the advantage is that the moment I write that equation in this form, that what is written on that upper right corner, then we are able to write it in the form of very easy form, like d square x is x by lambda d square, where we have put the value of lambda d as root over epsilon 0 kt by n square, and x we have put just r into phi minus phi 0. And the moment we reach this equation, all of you know what is the solution, and that results in the solution phi minus phi 0, that is x, that is equal to c by r exponential of minus r by lambda d. Why this constant is there? Actually there is a term x not positive also, but you know that positive term we need to neglect, because that potential cannot increase like that with r, so it has to decrease. So that is why actually we have taken this solution, and the constant, only one constant c is there, and we need to find out the constant c. Now you know that how to find out the constant c. Now there is a potential which is constant, which was constant throughout the plasma, that was plasma potential, that is phi 0, and the potential that is contributed by the charge, that is on the right hand side, that is c by r exponential minus r by lambda d. Now when you go very close to the charge, say delta r, and this delta r goes to 0, then you will be sure that you are going to get the Coulombic field of that positive q charge. And then what do you expect? That charge, the potential what you will get for that positive charge is q by 4 pi epsilon 0 into 1 by r. That is the standard formula. And where the exponential goes, because you have made the r tends to 0, so it becomes 1. So you are reaching the formula that it should be q by 4 pi epsilon 0 into 1 by r. And here what we have got, it is c by r. So what is the form of c? So this is nothing but q by 4 pi epsilon 0. So that way you find out that what will be the value of the constant, and you get an expression for the shielded Coulomb potential as phi equal to phi 0, that is your plasma potential when you have not inserted the plus q charge, plus q by 4 pi epsilon 0 r exponential minus r by lambda d. So what essentially it is giving, that as you are very close to the plus q charge, you are seeing the potential q by 4 pi epsilon 0 into 1 by r, that is a standard potential when there is no charge or anything in the surround. But because of the plasma assembly, that potential is getting screened by a factor exponential of minus r by lambda d. So this is the screening term, this is device screening term. Now what happens when r equal to lambda d? We see that the original pure Coulombic potential, it is getting reduced by 1 by e, and as per our physics convention, we say that after that distance, that is the length scale, lambda d, we will say that the effect of that plus q charge is almost over. So that is the device screening length, and lambda d expression is that is equal to square root of epsilon 0 k t by n square. K is the Boltzmann constant, n is the number density, and T is the temperature. So you can see that higher the temperature, higher the device screening length. This is quite expected, because when you are giving more energy into the plasma, and the particles are very energetic, they are moving at higher and higher speed, so naturally the length over which they will be able to maintain their charge neutral will be higher. But it is not linear, it is proportional to square root of t. And again, as you increase the number density, then what we see that device length is decreasing. This is why, this is because when you are increasing the number density, within in a smaller zone, larger and larger number of particles are coming together, and these particles includes both positive and negative charges. So that is how within a shorter distance they are able to maintain their charge neutrality. So that is why lambda d is decreasing. So this is how the device screening appears, and now we are able to achieve an expression for this device length, and that is proportional to the square root of temperature and inversely proportional to the square root of density. So now we are basically reaching a criteria for plasma state. So what is that? That length of that plasma. Suppose we have a plasma and you find that Debye length is more than the dimension of the plasma that is created. Definitely, you will never get the charge neutrality over there, and as you know that charge neutrality is a macroscopic charge neutrality is a major criteria to form a plasma, and that is not being there, so it will not be so is plasma behavior. So the first criteria is that Debye length for the kind of temperature that you have reached and the kind of number density that you are able to reach must be much less than the dimension of the plasma object that you have created. I will give you very popular example, and many of the times you will see that a question is coming whether the candle flame can be considered as a plasma or not, and they will be giving you certain number density of these charged particles and the kind of temperature that is available there. So what do? You just simply calculate the lambda d, and it is just over epsilon kt by n square, and you will see that because of the so low number density and so low temperature, not so low, temperature is moderate actually, you cannot touch it by hand, but the number density is very less, and because of that you will see that the Debye length is much higher than the dimension of the candle flame. So the first criteria, dimension of the candle flame is much less than the Debye length that you have calculated. So definitely it is not going to form a plasma. But same study you can do for other plasmas like ionosphere, like solar plasma, like fusion plasma, or arc plasma, or glow discharge plasma, and you will always see that this criteria, that Debye length is much less than the dimension of plasma, is always satisfied. Now I come to the second one, actually the number of particles inside the Debye sphere. So you have calculated one Debye length, and 4/3 pi lambda d cube will give you the Debye sphere, and you know the number density. So you multiply the volume by the number density and you will get the total number of particles within the Debye sphere, and that should be much greater than 1, because if only one single particle is present there, electrons or ion, then if a single particle cannot neutralize itself on its own, so you need to have large collection of both polarity particles so that they can shield themselves within the Debye sphere. So the second criteria is number of particles within the Debye sphere must be much greater than 1. So we get two criteria for plasma state, that is, one is Debye length must be much less than your dimension of the plasma, and number of particles within the Debye sphere, that should be much greater than 1. So next what I will discuss another very fundamental property of plasma, that is plasma oscillation frequency. So what is that? If due to some disturbance, that may always happen, electrons or ions are displaced from their equilibrium positions, then definitely the charge neutrality in that zone is disturbed and electric field will be created. That electric field, what it will try? It will try to bring the particles to their original position. But like a pendulum, when you take it from its equilibrium position and you just release it, then what it does, it goes to the equilibrium position but doesn't stay there, it moves further. That is because of inertia. Same thing happens over here. The charged particles, when they are disturbed, they try to come to their equilibrium position, but they overshoot. And then again they try to come to their equilibrium position and they overshoot, and the oscillation continues. So this kind of oscillation is called plasma oscillation, and the frequency is called plasma frequency. Now, more the particle density, higher will be the string force, because that electric field, you can apply the superposition principle to find out. So more the charge, more will be the electric field. Consequently, the higher will be the frequency of oscillation. So similarly, that the mass of the associated particles, more the mass, so they will be less will be the frequency. Like if you consider the charged particles, electrons or ions, so if they are disturbed, their oscillation frequency will be different if you go for these ions and the electrons. Usually, these electrons are so much mobile, as I've already told you earlier, that for movement of the electrons, the ion cloud almost remains stationary, kind of thing. So the features, plasma frequency is one of the most fundamental parameter, as I've already told you. Now, there are two types of oscillations inside plasma. One is high frequency and one is low frequency. High frequency oscillations are due to electrons, and they're so fast that the ions cannot follow them. For electrons, plasma frequency usually lies in the range of gigahertz. On the other hand, ions inside the plasma can support very low frequency oscillations. Now, two important things that should be always kept in mind, that the electrons are so fast that the ions can be fairly assumed to be stationary for these oscillations. And the ion oscillations are so slow that the statistical distributions of electrons surrounding an ion can be assumed to be static during their oscillation. So these are very two interesting things in plasma. Electrons are moving so fast that ion background, what is there, that is more or less stationary kind of thing. Whereas for the electrons, for the ions, when they are moving, they are moving slow that whatever movements their electrons are doing, they are more or less making a stationary kind of configuration. So here we give you a simple derivation of plasma oscillation frequency. So on the left hand side, what we have shown, it is a very uniform distribution kind of this thing, charges. It is idealized, it never happens like that. So here what is this, that number of positive and negative charges, they are all, and they are so uniformly distributed that there are no additional electric field is getting created just now. But if you do apply an electric field in such a way that the electrons are getting displaced, but the displacement is not uniform. If it would be uniform, then some electrons will be going out and some electrons will be coming in into that control volume, and what you will get actually, you will get again the charge neutrality maintained over there, and there will be nothing happening as such actually. But if there is a displacement which is non-uniform, that is, the displacement of the electrons is a function of the position, in this case it is in the x direction, and we are creating the disturbance only in the x direction, and y and z direction we are not thinking of. So if any oscillation takes place, that will be in the x direction only. So the disturbance is very fast and only the electrons are able to respond, and we assume that the ion background is staying as it is, as in their previous case. So the control volume I have shown there on that upper right figure, a small box, and in that you know that x direction we are making that non-uniformity in the electron distribution, and y and z direction they are identical. So you know that net accumulation of charge inside that control volume will be delta psi by delta x, that into delta x. So that is the net accumulation of charge inside that control volume, and if you multiply by delta y delta z, that will give you the volume over which you should count the net charge that is created due to this process. So if you multiply by number density n and electronic charge, you actually get the net accumulation of charge inside that control volume due to non-uniform displacement of the electrons. So the Poisson's equation inside the control volume read as divergence E is equal to delta rho by delta V, because that is the charge divided by the volume, that will give you the charge density, and divided by epsilon 0, as usual the Poisson's equation. Now we are creating the disturbance only in the x direction, so divergence E results in delta E delta x, and you reach a formula of that kind actually. Now solution of that is E is equal to n E by epsilon 0 into psi. Now when you know the electric field that has been created due to the accumulation of charge, then what you get? You know the force that is acting on the electrons, and that will be charge into electric field. So F equal to minus C into E, and that results in minus of n square by epsilon 0 into psi. Now you see that you have a force equation which is related with the displacement by a negative sign, like F equal to minus kx kind of equation, and you know that if that is the kind of force relation, then the frequency becomes 1 by 2 pi root over k by m, where k is the spring constant. So exact analogy like the spring, here also you are seeing a displacement which is negatively connected with the force through a constant, and that constant is root over it is n square by epsilon 0. So you can get the frequency, otherwise also you can solve this equation and find the frequency, and that is coming to be 1 by 2 pi root over k by epsilon 0. So that is ultimately giving you the plasma oscillation frequency as Fp is equal to 1 by 2 pi root over n square by m epsilon 0. So that is the plasma oscillation frequency with which it will oscillate. And you see that the plasma oscillation frequency that we have just now derived, it depends on the number density and the mass of the particle. Okay, so it is proportional to the square root of number density and inversely proportional to the square root of mass. So now we actually you know that electrons inside that inside a plasma are going random collisions, and the collision frequency should be much less than the plasma oscillation frequency, so that plasma can exhibit its collective behavior. This plasma oscillation frequency is basically a collective behavior, reflection of the collective behavior of the plasma. So we reach a third criteria for plasma state, that plasma oscillation frequency should be much greater than the collision frequency. If that doesn't happen, then plasma will never be able to show its collective behavior. That is very essential for plasma to show its characteristics. Okay, so up to this, we will meet you in the next class.